Now, responsiveness is not something that the respiratory system is doing. That's something that another system is doing, which happens to be a control system and will in turn cause you to ventilate more or less.
Central nervous system?
The nervous system, yeah, is providing the responsiveness. But just, strictly for respiratory, we've got movement, we've got excretion.
What about boundaries?
Yeah. Yeah, the respiratory membrane is a boundary. What is it separating?
The in and out.
The internal environment with the blood on one side of the wall, and the external environment, what's actually inside the air sac, right? That's all part of the external environment. Besides actually breaking down materials from the external environment, which is to digest, that's to break down, what is the other key function of the digestive system? We are digesting for what purpose? It's a means to an end.
Nutrients.
We can't do this other thing without first digesting these raw materials. Absorption. Absorption. Right? So the digestive system provides digestion and in turn absorption of nutrients, of materials from the external environment. Which of these necessary life functions can you connect to the digestive system?
Excretion, movement.
Yes, so we bring things in to one side of this tube that runs through the body, and other things go out the other side, things that we don't need. Movement, all right, explain the movement. Peristaltic contractions. We actually move the food stuff through this long tube, right, through the digestive tract. What tissue do we use to produce movement? It's one of the 4 primary tissues. We're doing that connecting thing again. Muscle. All right, what type of muscle? Smooth muscle. And when you use smooth muscle and you contract at one end, and that contraction as a wave passes down to the other and pushes the stuff in one direction, that's peristalsis, peristaltic contraction. Anything else? Clearly digestion for the digestive system.
Metabolism.
Yeah. What reactions are going on? Because metabolism simply refers to any reactions occurring and all reactions occurring in the body. Which chemical? They're all chemical reactions. Hydrolysis, right? Catabolic, those catabolic reactions, breaking down the proteins, complex carbohydrates into their building blocks. Yeah, it's all hydrolysis. But metabolism, absolutely. What do you notice after you eat a large meal besides feeling sleepy? It has to do with metabolism increasing, the rates of these reactions increasing as you digest the meal. You get warm. It's the thermogenic effect of digestion. You get warm. As all those reactions speed up, as you process all of those raw materials. Is there a boundary involved in the digestive system? The mucous membrane, right, that lines the digestive tract acts as a boundary, separating the external environment, anything that's in the digestive tract, from the internal environment, what's on the other side of the epithelial lining of that tract. What does the mucous membrane consist of?
Water.
Two basic tissue types. I know all 4 are actually there, but what are the 2 major tissue types, making this as some say, the simplest of organs?
The water.
Tissue types.
Oh,
What 2 tissue types? Epithelium, and what underlies every epithelium in the body? Connective tissue. What type? You know this now too. Areolar connective tissue, yeah. So in the areolar connective tissue, rich blood supply. So you don't have to cross the entire mucous membrane, you have to cross the epithelium. And as soon as you do that, you're in that connective tissue, you're gonna find your way into the blood. Besides moving things through the body, through these tracts, what other types of movement are required? What else do we need to be able to do? Again, necessary life functions. Just expanding on movement. You have to be able to move your body parts to manipulate objects in the external environment, and you need to be able to move your body. Locomotion. What is homeostasis? It's a state, it's a condition. So what you're doing is you're describing the state of the body at this time. You are maintaining a relatively stable internal environment. And you can leave it at that, or you can say, despite a constantly changing external environment. Because if it didn't constantly change, we wouldn't need to respond to it. We wouldn't constantly change. But our internal environment will if we don't do something about it, if we don't prevent those changes. So what's the first step in preventing changes in those variables that have to be kept in a narrow range? You can't do anything about the problem if you can't detect it. Who does that? Who's detecting the problem? Who's monitoring the environment? The receptors, sensors. And if it's the nervous system, we do call them receptors. If it's the endocrine system, it's the endocrine cell, not a separate receptor. The endocrine cell itself is acting as the sensor and the control center. I can map that out. So my version looks different than the author of our book's version. So if the endocrine system is responsible for this, the endocrine cell takes care of these two things. Acts as the sensor, acts as the control center. If it's the nervous system, you have neurons in the brain or spinal cord in the central nervous system. And that group of neurons is acting as the control center. But they are receiving signals from other neurons who form the receptor. Right? So the neuron that forms the receptor is going to signal the neurons that form the control center. Two separate entities. But when it's the endocrine system, the endocrine cell takes care of both. And this only works if the control center has a built-in. The control center only knows if there's a problem if it has a set point. So we usually show that as a double arrow, meaning it's going to make a comparison between what it's supposed to be and what it currently is to determine if there's a problem that needs to be fixed. And if there is, the control center communicates with the effectors. Right? And it's going to be effectors, multiple. So the example that we spent the most time with, thermoregulation. Starting with thermoregulation in your house, with your thermometer, your thermostat, your heater, your air conditioner, right? And seeing that the thermometer is the receptor, the thermostat's the control center, your AC, your heating unit, those are the effectors that fix the problem. In your body, what are the receptors called? So in your house, thermometer. In your body, thermoreceptors. All right, so when I have you illustrate negative feedback loops, I'm not looking for the basic components of any negative feedback loop, receptor, control center, effectors. I'll be asking for the names of these things for a specific negative feedback loop, like thermoregulation. Right, so for thermoregulation, in place of receptor, you're going to put thermoreceptor. What's the control center when it comes to thermoregulation in your body?
Temperature.
You can give me the brain. The brain's the control center, that works. You could get more specific. In the brain, it's the hypothalamus. So thermoreceptors are going to communicate with the hypothalamus, the brain. And in turn, if there's a problem, the hypothalamus is going to send signals to, I mean, you can put the word effectors, that's fine, but you need to tell me what they are. We can do a list. How many are there? How many effectors for thermoregulation? 3? So instead of just putting muscles, be more specific. Which muscles? Just skeletal. Not smooth, not cardiac, just skeletal muscles. Sweat glands?
Blood vessels. Blood vessels.
Oh, I'm glad you put it that way. Blood vessels, you would get half credit. Because if that's all you put, that implies all your blood vessels. And that's definitely not the case. You need to be specific. Which blood vessels? Skin. The term that means skin? Cutaneous. So don't just put muscles, don't just put blood vessels, too vague. You need to know which muscles and which blood vessels. I don't need to know which sweat glands because it's all of them. You're okay with that one.
What about putting epidermis? Is that wrong?
Epidermis?
Yeah.
Epidermis doesn't change what it does in any way. It's just a structure.
If you could add on the exam, would that be half credit or not?
Oh, like epidermal blood vessels?
Right.
But there are no blood vessels in the epidermis. Remember, epithelium is avascular.
Oh, I got you.
So when we say cutaneous, that's the epidermis plus the dermis, right? That's the cutaneous membrane. And the blood vessels are specifically in the dermis, in the areolar connective tissue. But you don't have to do all that, just cutaneous blood vessels. You could even just put skin blood vessels, that's fine. Now, is it the same 3 effectors, regardless of the problem? Does it matter if the problem is we're too hot or too cold? No, same 3 effectors. What they do is different. Same 3 effectors. So you have a drop in core body temp. It's detected by the thermoreceptors. They signal the hypothalamus, compares the set point, detects that the temp is too low, signals the effectors to produce the appropriate effects. What are the skeletal muscles going to do in this case? So increase contraction. And for this to make sense, you have to realize that your muscles, even when they feel relaxed, are never truly relaxed, not totally. Low-level contractions are occurring within your skeletal muscles all the time. It's called muscle tone. We all have muscle tone. And the only way for your muscle to go completely relaxed, cut the nerve. But your nerves always are sending signals to the muscles, right? Just low level. If you're cold, we're going to increase those signals, right? And the muscles begin to contract more forcefully, to the extent that you might even feel it, right? And when you feel it and see it, you call it shivering. But if I ask, what are the, because you need to be able to tell me not just the name of each effector, but tell me what it's doing in order to produce the effect. If you just put shivering, you're not really explaining what's happening. Right? Shivering is just this thing. Okay, but what is that? I want to know what that is. Right? Increased metabolism in the muscle, increased contraction. And really, the whole point isn't to contract, it's to increase the metabolic rate of the cell. That's what we're really trying to do. Now, what's the effect going to be? And then we'll bridge the gap. This is easy. It's the opposite of the stimulus. An increase in core body temp. All right, so get me there. Muscles are stimulated. Put the little plus sign. We're going to stimulate the skeletal muscles, increasing the metabolic rate. How is that going to lead to increased core body temp? Increased heat production. Right, that's the key point right there. Sweat glands. Are we stimulating them? Are we inhibiting them? We don't constrict or dilate, that's blood vessels. We stimulate or inhibit for skeletal muscles and for sweat glands. We're inhibiting. As a result, what happens?
Less heat goes to the...
Okay, so decreased sweating, less water on the surface of the skin, therefore less what? Decreased heat loss through, how are we reducing heat loss? Right. We are slowing down evaporation of water on the skin. Right, so maybe the sweat glands were slightly active before. Now we're going to completely shut them down. No more water on the surface and get that evaporative cooling minimized. So decreased heat loss via evaporation. Or you could say decreased evaporative cooling. And then this helps to increase core body temp. Cutaneous blood vessels, what are they doing? So we can't say stimulate or inhibit. But we can say constrict or dilate. And if you're cold, what do we need to do? So that's vasoconstriction. Constriction of the vessel. All right, does vasoconstriction increase core body temp? Kind of, but get us there. Vasoconstriction does what, which in turn increases core body temp? No? I mean, yeah, it does increase blood pressure, but that doesn't help us get warm or cool.
It decreases the heat from escaping.
Okay, so decrease blood flow to skin, decreasing heat loss from skin. Through what mechanism? So with the inhibition of sweating, we are reducing heat loss through evaporation. Here we're reducing heat loss from the skin through radiation. And if you have a fan on, convection. And if you're lying on a cold tile floor, conduction. Right? These are all means of heat transfer. So you don't have to give me all of them, just radiation is fine. Decrease heat loss from skin through radiation. You could say decrease radiative heat loss. we only did these two things, inhibit sweat glands and vasoconstrict the cutaneous blood vessels, would we increase core body temp? Because what is needed, but neither of these mechanisms provide it? Generation of heat. All they can do is take the heat we're already generating and make sure we lose less of it, which is important. But arguably, maybe the most important thing here is increasing heat production by stimulating the muscle. Now, what would be the problem, potentially, if you only stimulated the muscles and you didn't inhibit sweating and you didn't constrict the cutaneous blood vessels?
You'll be losing heat as fast as you're making.
That's very possible. That all this extra heat that you're making, you would just end up losing, right? So we want to do both. Make sure we're increasing heat production, but also reducing heat loss. That combination is what brings the core body temp back up. If you're too hot, same thermoreceptors, same control center, hypothalamus, same effectors. Now what happens to skeletal muscles? You're too hot. What's the opposite of a plus sign? And you're going to inhibit them to accomplish what? So you inhibit the skeletal muscles to decrease metabolic rate, right? Decrease contraction, which decreases heat production, which increases core body temp, or can help increase core body temp, right? That alone won't be enough. Sweat glands will be stimulated. Sweating will increase, increasing heat loss through evaporation, which is going to help bring down core body temp as we increase heat loss. Cutaneous blood vessels will dilate, increasing blood flow to the skin in order to increase heat loss through radiation and potentially conduction, convection as well. Good with negative feedback? What were the two examples of positive feedback we looked at?
Parturition and blood clotting.
Parturition and blood clotting. Tell me about the inorganic molecules, chemicals. What do they include? Chapter 2. We separated chemicals into organic and inorganic. What's inorganic? Not what does it mean, but what are the categories we actually look at. What it means is chemicals that don't use carbon or hydrogen as their primary structural components. That's inorganic. But what did it include? Oh, that's not a good sign if you have to look this up. You should have known this coming into the class. Acids, bases, salts, water. Those were the major categories. What did you need to know about water besides it's inorganic? It's polar. It's held together with hydrogen bonds, right? The water molecules, absolutely. And so what were the resulting characteristics of water? Or we could call them the resulting vital properties of water as a result of the polarity, the hydrogen bond. Universal solvent, chemical reactivity, high heat capacity, and related to that, high heat of vaporization, lubrication, cushioning. So how many vital properties? 5. So tell me about lubrication cushioning. What does that refer to? So you can use examples.
Serous fluid.
Cerebrospinal fluid provides a cushion for the brain and the spinal cord. They literally float in water, and that actually reduces their weight by 97%. And they're such delicate tissues that if they were not floating in water, their own weight would crush them. The bottom of the brain, the bottom of the spinal cord would be crushed by the weight of the organ itself. Because it doesn't have any strong internal framework, right, to give it structure. It's like gelatin. It can be described as like oatmeal, right? That's the consistency. So it's very delicate stuff. Any other examples?
Synovial joints. Are we looking for cushioning?
Yeah, see, what really provides the cushion is the cartilage itself, but a big component of that is water. Guess who it is? My mom. I'll let her off this. She does that when I'm actually teaching all the time. I'm like, you know my schedule doesn't ever change. It's been years. I'm sorry. She doesn't know today. What the heck are you doing at work? I'll say, I don't know. Good question. But I am trying to sell a car. Anyone want to buy a Prius 2012? 67,000 miles? 13,000 bucks. It averages 58 miles per gallon. 8 miles pure electric. If you're just doing, stuff in the neighborhood, don't have to use gas at all. Think about it. Let me know. Gotta unload it soon. It's kind of a spontaneous buy, yeah. So now it's gonna be a couple weeks before it comes in, so I got some time to sell it, but gotta sell it. Where were we?
Water, lubrication.
Synovial joint, cartilage. Cartilage has a high water content. So in the end, yeah. How about lubrication?
Membranes.
Serous fluid, serous membranes. The fact that they can slide past each other without friction, without rubbing because of that fluid between them. High heat capacity. I don't know that you could really give an example for this one like you could lubrication and cushioning. This one's more just explaining what it means. What does it mean to have a high heat capacity?
You don't evaporate absolutely?
It means this substance has to absorb a lot of heat. In order for its temperature to go up, it has to lose a lot of heat in order for its temperature to go down. So why is that ideal for us? Because we're trying to keep temperature stable, right? So that's a great characteristic. It also means there's a high heat of vaporization. So in order to actually convert the water on your skin into water vapor, you're going to need a lot of heat to do that, right? That water has to absorb a lot of heat for its temperature to increase enough for it to become vapor. Well, where's that heat coming from? This lot of heat. From you. Perfect, right? It's a great mechanism for heat loss. Knowing that a ton of heat is going to have to be removed from the body to convert this water to vapor. So evaporative cooling, extremely effective. Dogs can't do it though, unfortunately. So what do they do instead? Panting. Panting's not very effective for us for heat loss. That's all they've got. Universal solvent.
Water.
Yes, water is a universal solvent. What does it mean?
Dissolve.
I hope you don't put that as your answer on the test.
Dissolve.
Describe universal solvent. Water. Okay.
Dissolve other poor substances.
Most of the substances in the body, needed by the body, are water soluble. And we've got a workaround. For the ones that aren't, for the lipophilic substances, we can bind them to something that is water soluble. Something that can carry these things around the body as needed. What are those things? That can have a region that's lipophilic and can bind to a lipid, and then the rest of it's hydrophilic, so it can dissolve in water and carry this thing around. Protein. So one of the many functions of proteins is to act as a carrier in the blood. So what would be a chemical messenger? That would require a carrier. They can't just dissolve in the blood. So I'm talking about a hormone, right? Hormones are chemical messengers that use the blood. So what type of hormone can't just dissolve in the plasma and circulate by itself? Has to get attached to a carrier protein.
Cholesterol?
Yes, which is it's an example of or the main example of
Hormones.
steroid.
Steroid.
Yeah, so steroid hormones. All steroid hormones have to bind to carriers in the blood. Now there is one hormone that's not a steroid, but behaves like a steroid, is lipophilic like a steroid, and therefore requires a carrier, and that's thyroid hormone. And I only bring that up because one of the proteins used as an example for quaternary structure in the chapter 2 slides was a protein called transthyretin. That happens to be a carrier for thyroid hormone. It has 4 subunits. Did we get them all? One more. Chemical reactivity. What does that refer to? Really means 2 things. Hydrolysis is an example of what? So that was a big jump, but you're right. All right, so chemical reactivity refers to the fact that water participates in many chemical reactions. Example, hydrolysis, dehydration synthesis, right? Those are examples. But it also reflects the fact that, because it doesn't have to be a participant, it doesn't have to be involved in the reaction, but all reactions have to occur in water. So that's kind of the 2 part of chemical reactivity. Water is a participant in many chemical reactions, but also all chemical reactions occur in water. Biggest body cavity. Ventral body cavity is the biggest. What do you find in the dorsal body cavity? The brain and the spinal cord. But yes, we can subdivide the dorsal body cavity into the cranium, or cranial cavity, and the vertebral column, or vertebral cavity, or even spinal cavity. And then you can subdivide the ventral body cavity into thoracic and abdominopelvic, and we actually do have a structure that separates the 2, which is the diaphragm. And then the thoracic cavity can be broken down into how many smaller cavities? 4. So 2 of them are pleural cavities, one on the left side, one on the right. So if we kind of go through the progression, it would be taking the thoracic cavity and dividing it into 3 sections, right? So pleural cavity left, pleural cavity right, mediastinum down the middle. But then we do end up dividing the mediastinum because the bottom half of it is its own little cavity that contains one organ, the heart, and that one's called pericardial cavity or pericardium, leaving you with just now the top half of the mediastinum, which we now call superior mediastinum or mediastinum. Abdominal pelvic, no true delineation between abdominal and pelvic. Right, so we usually just combine them. It's a big area though, so how do we break up the abdominal pelvic cavity into smaller portions so we can more easily describe where something's located? We can go with quadrants. How many quadrants are there?
4.
Quadrants?
4 quadrants.
Five quadrants.
I know how to do
How many regions?
9.
9. Where do you find the bladder? What quadrant? In what quadrant do you find the bladder?
The bladder is.
And this is why we don't use quadrants to describe the location of the bladder. Half of it's in the left
Yeah.
lower and half of it's in the right lower. So we go with region. And the region?
Endogastric.
You can go with hypogastric, or you can go with pubic. Which membrane or membranes separates the internal and external environments? Which membrane or membranes separates internal and external environments? Serous does not. Serous has nothing to do with forming boundaries. It's all about protection of moving organs, right? So that there's no inflammation. I guess I should have started with the easier question. How many membranes do we have? And what are they called? We have 3. We have mucous membranes, serous membranes, and the cutaneous membrane. All 3 of them are epithelial membranes. Right? So we can start with what are the membranes or epithelial membranes of the body, and then it's those 3. And then I'm asking which one or which ones separate the internal and external environments. Cutaneous. That's it? Cutaneous? There's no other way in or out? We'd be screwed if it was just cutaneous, because almost nothing goes in or out of our internal environment through the cutaneous membrane. Almost nothing. Almost all of it goes through the mucous membrane. So that means you forgot about the tracts. What's inside of the tract is the external environment. And the boundary between what's inside the tract and the internal environment is the mucous membrane. Don't forget about the mucous membrane. How many chromosomes in a typical body cell, a somatic cell?
46.
46? How many different types of chromosomes within a typical body cell? 23. 22 of which are called autosomes. The 23rd pair, the sex chromosomes, right? The X and Y. We say 23 pair because for each of the 23 types, you have one from your mom and one from your dad. So from chromosome pair 1, a maternal and a paternal. Chromosome pair 2, a maternal and a paternal, right? That's 46. And we say 46 different chromosomes because the paternal chromosome 1 and the maternal chromosome 1 are different, right? They're not the same. 46 different chromosomes in all. And the name that means that, it's a way we can describe a somatic cell, and it reflects the number of chromosomes it contains. Diploid, or the numerical notation, 2n. And n always means number. N represents the number of what? Different types of chromosomes. How many different types of chromosomes are there? 23. So 2n is 2 times 23, 46. And if you have only one representative from each pair, only a paternal or a maternal chromosome, 1, 2, 3, all the way down the line. If you only have one from each pair, then how many total chromosomes are in this cell? 23. And what do you call that cell? The term that means 23, the term that means half the normal number. Haploid. Or instead of 2n, it's n, right? You just get one of each. 23 different types, one of each. Which cells are haploid? Only one type of cell in your body is haploid, your sex cells. Your egg cells, your sperm cells.
Only one cell has a
That's true.
I don't know.
What are the 3 types of membrane specializations, membrane extensions? Where we take the cell membrane and we do something with it, fold it into something. So we have microvilli, we have cilia, and we have the flagellum, right? And only the sperm has the flagellum. Function of cilia.
Moves to across the, oh, wait.
Move substances across the surface of the cell. Microvilli,
Increases surface area.
right? These don't move, so movement's not the thing, it's surface area. Not to move substances across the surface, but to increase surface area, typically for transport, right? To move things in and out of the cell. With more surface area, you have more transporters. You can move more substances. What type of chemical bond do you find between the amino acids in the primary structure of your protein? What type of chemical bond joins the amino acids of your protein? Say again? Covalent? Yes. The name is peptide. The type is covalent. The name is peptide. Absolutely. How about between the nucleotides of a nucleic acid? So I'm talking about within a strand of RNA, within a strand of DNA. What's holding those nucleotides together? Covalent bonds. And they don't have a special name like peptides, just covalent bond, just the type. Now, you've got your strand of nucleotides in the form of, say, your coding strand of DNA. Another strand of nucleotides, your template strand of DNA. What joins the template strand to the coding strand?
Hydrogen bonds.
Hydrogen bonds. The previous question was, what's holding the nucleotides together in a strand of DNA or a strand of RNA? Covalent bonds. I answered it?
Yeah.
I thought so. What type of bond is used to fold a protein but is easily disrupted by excessive heat or acidity? So it's got to be a weak one. Hydrogen. So when we denature a protein, the bonds that are being disrupted are specifically the hydrogen bonds. Excess hydrogen ions can disrupt these hydrogen bonds. So that's why too much acidity is a problem. Heat can do the same thing. So to denature a protein is to unfold it, right? To unravel it. What type of chemical bond involves attraction between opposite charges? Ionic bonds? Yes. Any others? Involves attraction between opposite charges. We can draw it for you.
Is it polyvalent?
Too close together, darn it. That one.
A little oxygen.
Hydrogen bonds are attractions between opposite charges. The positive charge of the hydrogen side of a water molecule, but the negative charge of the oxygen side of a water molecule. So hydrogen bonds and ionic bonds are bonds created by attractions between opposite charges. Covalent bonds, very different. What's going on there? What's joining the atoms together? Sharing of electrons. So what type of bonds is used to form a molecule of water?
Well, I'm sorry, what was
What
the
type
question?
of bond is used to form a molecule of water, to form an H2O?
Covalent polar.
Covalent, and it happens to be polar covalent. What type of bond joins individual water molecules? Hydrogen. Right. If a solute is hydrophilic, what happens to it when you put it in water? We say it dissolves, but what does that mean? What's happening to it, quite literally?
Disassociate?
If it's an ionic compound, it's going to dissociate. But I'm saying like just a hydrophilic solute, like water, or an ion. Put the ion in water. Put a glucose in water. So it dissolves, but what's happening to it that makes it dissolve?
The water starts coming in and separates the.
So that's going back to an ionic compound. We can start there.
It goes down? Are you
So-
talking about concentration?
No. So instead of a glucose, let's do that. So salt, sodium chloride. Salt tablet, crystal form, put it in water. It dissolves, it dissociates, right? And what's happening? You were getting there.
Yeah, the water molecule starts surrounding the
Yes.
other molecules, vibrating.
Right. So water molecules start surrounding the sodium ion. Water molecules start surrounding the chloride ion, separating the chloride ion from the sodium ion. Right? So they're no longer joined. All you have now is just those individual ions. So if I just put an ion in water or just a glucose in water, what's happening? Water molecules are surrounding it. If they don't surround it, it doesn't dissolve. What's that called? Where you have the substance and the water molecules surrounding it. A hydration sphere. So if it's hydrophilic, hydration spheres will form around it, thereby dissolving it in water. What type of transport is used to move potassium out of cells? What type of transport would you have to use to move sodium out of cells? What type of transport? There's often many ways to answer it, and it's fine as long as it's right. Facilitated diffusion to move potassium out? Because what does it require? If it's just diffusion and not pumping, what do you need? Concentration gradient. It's all you need for diffusion, right? Just a concentration gradient and the thing will move from high to low. So if you said facilitated diffusion, that tells me that you know that potassium is more concentrated in than out, right? Because I asked what type of transport moves potassium out of the cell. What type of transport moves potassium into a cell?
Would it just be simple diffusion?
That one has to be active.
That's wrong on two accounts, because sodium's not lipophilic, nor is it moving down its gradient.
So it has to be a pump active.
All right? Primary active transport would be used to move potassium into a cell. That's exactly right. In fact, which transporter does this? The sodium-potassium pump. Exactly.
Hopefully those will be multiple choice.
It's all right. You've got time. It's not till Tuesday. It's good that we're doing this today and not Monday night. Let's see. We can come up with a few more. How do we get a steroid hormone into a cell? What type of transport would be involved in the movement of a steroid hormone into a cell? Assume, by the way, that the concentration of said steroid hormone in the cell is 0, right? And there's a lot of it in the blood. So there's clearly a gradient for this thing to go from the blood across the capillary wall into the cell. where there is none of this steroid bond. So that it's got a gradient, but describe the type of transport that's involved. So that's a lot of information right there. The fact that there's a gradient tells you it's passive.
Simple diffusion.
It's diffusion.
Simple.
Simple diffusion. Yeah. Because a steroid is lipophilic. What type of transport are you using if you're moving one solute down its gradient and one against? So one transporter is moving both, but one's going down, the other's going against its gradient.
Secondary.
Secondary active transport. Moving two solutes both down their concentration gradient. Facilitated diffusion. Moving two solutes both against their gradient. Primary active transport. So when they're both moving against, what's the source of energy? What's the driving force?
ATP.
If they're both moving down, what's the energy? What's the driving force?
Pressure.
Concentration gradient. The kinetic energy of the concentration gradient. If one's moving down and one's moving against, what's the source of energy? So this is secondary active transport, right? And the energy is coming from concentration gradient of the solute moving down its gradient. The kinetic energy of the concentration gradient of the solute moving down.
But that still depends on the primary function.
That's right.
In our work.
That's right. But the transporter that's moving these solutes itself is not using ATP. Right? But it is still active because at least one of the solutes is moving against its gradient, so secondary active.
It's still using the ripple effect of the primary one.
Yeah. So that's why we say that secondary active transporters are coupled to primary active transporters, thus using ATP indirectly. Because when the primary active transporter stops, you lose the gradient of the solute that you are using for secondary active transport. Give me some homeostatically regulated variables.
Blood pressure. Blood pressure.
Blood pressure, yes. What else? Blood what? Yes, temperature, core body temp.
Heart rate.
Most of them can start with blood. Heart rate. Do we have receptors for heart rate? And this is a way to figure out, if you're unsure, this is a way to figure out if it's a homeostatically regulated variable or not. If it is, that means it's controlled by a negative feedback loop, which also means there must be a receptor for it. So do we have any receptors monitoring heart rate? We do not. Heart rate is not a homeostatically regulated variable. If it was, it would be relatively stable, but your heart rate goes like this all day long, right? All the way down to maybe the 50s for a resting heart rate while you're sleeping, up to the 150s when you're running from the tiger chasing you at the zoo. Going, yes, taking the exam. So changing heart rate is actually a means to keeping some other variable relatively stable. We change heart rate not to change heart rate, to change something else that is a homeostatically regulated variable, which is blood pressure. So if your blood pressure is falling, one of the effectors is the heart, and what it does to fix that problem is it starts beating faster. Heart rate goes up, and it beats more forcefully. Stroke volume goes up. The amount of blood it squeezes out goes up. So now more blood leaving the heart at a faster rate, pressure builds. What else? Blood glucose levels, pH, osmolarity, electrolyte levels, or you could say ion levels, O2, CO2, gases. Anything else? Last minute? You got 5 left. I'm going to require some home-baked goodies next time. Yeah, this is not
Oh,
good.
that's where you were going with the cup.
I didn't want to come out and say it. But
Kind of wondered.
wouldn't be the worst thing.
If I do ribs, do I get extra credit?
Ribs will work. I'll do ribs.
Too much work.
You know how many ribs I'd get if they were worth extra credit?
Yeah, but
Pounds and pounds.
I don't know.
Every class. I might give you a hug, but not extra credit.
Well, that's why I do it for gratitude.
You do it for hugs. Anyone not sign the sign-in sheet?
Does anybody want to have a study group tomorrow? Yes?
Yes, I
I'm gonna
will.
send out an email